In this series of videos I'm designing a Z80 based computer system, and this series of videos is really intended to promote a book I'll be releasing at the end of this series, which details all the circuits and the thinking behind the circuits. But what this video series and the book are really about is how to go about designing a system like this. It's not really specifically about this system, but I do go into detail for each circuit by way of example, and all the schematics, everything else are in the book. But what I want to discuss in this particular video is the systems approach to design. Now, I'm sure that systems design means different things to different people, but what I'm referring to when I use the term here is designing a circuit in such a way that it best suits the system I'm currently working on. And that's what I've done with this circuit. Now, if you don't recognize it, these two circuits are the transmitter and receiver for the RS232 module for our computer. And I've shown two different circuits for this, and the book shows both and explains them both in some detail. The first one was kind of a universal design, and it would work as a kind of standalone circuit, but the second version, the version I've got here, is more a systems designed version. Very similar, but there are some significant differences, and I want to just point out what these are. Now, I've done the same thing throughout the design. I've done the same thing with the video output, and as some of the commenters were struggling a bit with the concepts I was trying to get across. But the important thing to bear in mind is some of these circuits will not work in the way you may expect them to if you try and build them and run them standalone. They do expect to be used within the context of the system that I'm designing. Same with the video output. It was designed to work within the context of the system that I'm designing. Having said that, I'm presenting each of these elements as a completely separate entity, so you're free to design your RS232 or your video out however you want. Just bear in mind, what I'm trying to show here is the way that you can go through and treat them as separate projects. In fact, if you go on to the internet, you almost certainly find hundreds of circuits for RS232 or video, whatever else. Most likely they work fine, but things get very different when you start designing a complex system. You could put together various universal circuits, but it's not necessarily going to give you the best results. And in fact, I've had a lot of people along the way in this series suggesting I use a UART or this or that, other large-scale integration devices. Now, the stated goal for this project was to use discrete design for various reasons, partly so that I could more fully explain the way the system works, but also because for me it's more fun to do it that way. A benefit when you come to using discrete design, which I think is something that's kind of getting lost these days, is a well-designed discrete circuit can usually outperform a large-scale integration device in several ways. One in terms of its actual performance, but the other in its usage. The system I've put together here, the RS232 module, will be very much more straightforward to design software for than it would if we'd used a PIA and UART to drive this particular part of the system. The circuits are not as universal, but they are very well suited to this particular design, which is what I'm trying to get across in this video, is that that's a systems level approach where we don't need all the extra bells and whistles that we aren't going to use in the system. We just need the particular features that we require for our system. I was asked if the book went into composite video. No, it doesn't. We're not using composite video in this system, so I'm not going to bore people or confuse things by discussing elements that I'm not using. But what I'm going to do in this video is try and demonstrate two things. One is that you need to be fairly careful when you start looking at systems level design, but also the benefits it can yield if you want to design a discrete circuit. In fact, designing discrete circuits, I would say, is analogous to writing embedded code in assembly language, as opposed to using a high-level language. High-level language is analogous to large-scale integration devices. Assembly language is analogous to designing discrete component circuits. And just like with embedded code, when you get down into the weeds and start using assembly language, you get far more control over what the system is doing, and quite frequently you get much more performance. And anyone that's done any serious systems design will almost certainly at some point have had to use assembly language for certain modules, just because they needed that full control over the hardware that they were trying to write the code for. So what we'll do now is have a look at the system issue when I modified this circuit, and I'll explain what's causing it. But this is something I was aware of before I made the change, which is why I designed the two different versions of the circuit. So the first version, where I used 74161s for the primary counter, could be thought of as the universal version of the circuit, but then I modified it. I went down the systems design approach to simplify it, but that did require me to take into account other things that I will now demonstrate. So this is powered up. What I'll do is I'll bring the terminal up into the corner of the window, and I'll now enable the transmitter. So I've got the terminal set up. It's set to 9600 baud, and it's set up to suit the packet format of our system here. So this circuit on the right here is really the clock divider circuit that normally resides on the Z80 board. It's the primary divider coming from the clock, but I've included it here just so I don't have to have the Z80 board hanging off the end of this. But it's providing at the moment the 625 kilohertz clock to the circuit. It's fed with a 10 megahertz signal, which is equivalent to our 10 megahertz crystal on the main board, and it's just divided down to give us the 625 kilohertz clock signal. The main clock is already on, and what I will now do is enable the second channel on the signal generator, and it's just going to provide a series of pulses, low-gain pulses, that simulate the Z80 trying to load and send data out of our RS232 port. So if you recall, we start the process by taking the start line of the transmitter circuit low, and at the same time we provide it with a data value. Now the data value at the moment is provided by these yellow jumpers, and like I said, it's at the moment for easily for a JRK just by fitting or removing this jumper. So I'll now start the signal generator. You can hopefully see on the scope that we are now seeing data going out, and you can see on the terminal that the data is being received. And if I change this jumper, you'll notice that the data changes as well. You can see it change on the scope, and you can see it change on the terminal. Now at the moment the start pulse on this is 2 microseconds wide, which is a lot wider than we would normally get during a write cycle from the Z80. So what I'm going to do now is reduce the pulse width on the generator to give a 1 microsecond pulse width. So I'm doing that now, and you can see that the data being received is now incorrect, and also the data we can see on the scope is incorrect. If I go back up to 2 microseconds, you can see the data is fine. Just expand the scale a bit, but if I go down to 1 microsecond, you can see there is an issue. So I'm just going to explain what's causing this, and it's a fairly simple thing that's causing it, but it's again something that you need to be aware of if you're taking the systems level approach. So this is the general circuit for this, and the issue in this case lies with this particular counter. This is a bit of an odd counter. It's got a counter and a separate register, and they're not updated in sync. So look, there are 2 clock inputs. One is the clock input for the counter, and it increments the counter. The other clock is to latch the data that's come out of the counter into the register, and it's the register that feeds data to the output pins. But this arrangement means that if you clock these two together, then the output from the pins on the device are always one count behind the value in the internal counter. Now when you're going round and round, it doesn't really matter. The clock phase is not that important, but where it becomes an issue is when we reset this. So we reset this as part of the start process when we apply the start pulse to it, and that causes the internal counter to be cleared, but it does not clear the register. The register is only updated at the next clock pulse, which means that when the start pulse arrives, the counter is clear to 0, but the output from the registers is not. And it does not get cleared until the next clock pulse arrives, and we'll have a look on the scope as to what effect that has. So the signal looks fine here, and I'll just turn the start pulse width back up to 2 microseconds, and the data is once again as it should be. But what we'll do now is we'll zoom in to the start pulse. So the start pulse is the purple trace, so we'll zoom in. And we're now at 2 microseconds per division. So as you can see, we've got a 2 microsecond start pulse, and everything is working fine. We've got the correct data coming out, and you can see up on the yellow trace. The yellow trace is the clock being fed to the shift register, and it's only on the first rising edge that the output of the counter is clocked through to the register on the counter and then onto the output pins. And you can see there's jitter here. Some of you may already have guessed what's causing this jitter, but if I now go down to 1 microsecond, notice now that one of these clock edges is actually outside of the start pulse. So notice that if I do single captures, this particular clock edge, the yellow edge, is outside of the start pulse, and if we go even shorter on the start pulse, so I'll go down to about 300 nanoseconds, which is about what we'd get from the Z80, do another single capture, we'll zoom in a bit further. You can see that the rising edge of the clock pulse is even further out. Now the reason this causes a problem is because it means that the first clock edge that is received by the counter is, in this case, about 200 microseconds after the release of the start pulse. And that effectively means that the start bit that we're trying to feed out of the transmitter is only 200 nanoseconds long. If we zoom back out, okay, we've still got the same number of pulses, but notice that the data going out has changed. So if you look at this data at the bottom, you've got 2 high level bits followed by our normal data sequence. If I go down to 300 nanoseconds and we do another capture, notice now that the first bit is only 1 bit period long, and this is consistent. If I just keep doing single captures, you'll see that we're going from 1 to 2, and if you look at the instances where we're getting 2, and then if you were to zoom in, you would find they are the instances where the clock rising edge occurred before the end of the start pulse. It's quite hard to see because we're not capturing that much data on this, but in this case the rising edge of the yellow trace is before the rising edge of the purple trace. In other words, the first clock pulse being fed to the counter occurs during the reset pulse, and that causes the reset value in the internal counter to be latched into the output register, and then it's prepared now for the proper sequence. However, if we try again, do another single capture, in this case we've got the wrong data. If we zoom back in, notice that this time the rising edge of the yellow trace is outside the start pulse, and so the first bit is effectively this short period here, which is why it appears to disappear. The bit is actually still there, so that our two bits are still there, but the first one is so short that it is effectively ignored. It should be 104 microseconds and it's only about 200 nanoseconds. But when we get the proper position of the rising edge of the clock, we get that full start bit. So now we know what's causing it, how do we go about correcting it? Well, it's actually very straightforward. As I say, the circuit was designed from the systems level approach, so I already knew what resources I had on the Z80 board, the processor, and all we need to do to get rid of this is to guarantee zoom back in. We just need to guarantee that all the clock edges occur within the time period of the start pulse. Of course, a very easy way to do this, and the reason there's such a delay here is because this clock is being fed from a 625 kilohertz clock. But what we can do, look back at the circuit, is we can feed the register clock from a higher frequency clock, so that it's got more opportunities to effectively latch the value in the counter to the register. So all I did when I designed this circuit, when I'd switched to the 590, is run the register clock from a 10 megahertz source rather than the 625 kilohertz. We still need the counter to run at 625 kilohertz because that's what gives us our correct baud rate. But running the register clock at 10 megahertz means that it will feed the data through much more reliably. So I'll make that very small change now. We'll do another single capture, but notice now that the rising edge of the yellow pulse is well inside our start pulse, which the start pulse is still at 300 nanoseconds. We'll try a few more, and notice now every single time we are well within the purple start pulse. I put it into auto, and we can see now that we are always well within the start pulse. I'll just move the jumper back so we're running at 625 again. And now you can see the clock edges mostly occur, in fact they all occur outside of the start pulse. So we'll go back to 10 megahertz. And everything is fine. I'll bring the terminal back up into the corner of the screen, and as you can see, we are getting the correct data even with a 300 nanosecond start pulse. And in fact, we can go as low as around 120 nanoseconds on the start pulse now, and it will work fine. I started with the clock signals when I designed this circuit, and the reason for doing that is to make sure that the timing that we got was going to be correct. But if we take this circuit out and try and use it standalone with a single clock, then of course we would run into difficulties. So that's really what I'm getting at when I'm talking about system design. It's making sure that the various circuits will operate the way they're intended to, and also that they are optimized to work as reliably as possible. So having said that, we'll now see how fast we can run our RS232 interface and whether it's going to allow us to run at full speed. Okay, we've got the circuits set up, we've got the transmitter set, and we're driving it with our 300 nanosecond start pulse. It's got the 10 megahertz main clock going into this circuit, but as I said, this is normally part of our main board, and then the 625 kilohertz circuit is being used as the primary clock for the two counters, one for transmit, one for receive, and the 10 megahertz clock is being used to make sure we get proper operation of the counters. So what we can now do is try to get some idea as to the general performance we're getting. So you can see at the moment, as I said, this is set to 9600 baud, but you can see that at a clock or a start frequency of 300 Hz, we're sending 300 characters per second. So how can we go any faster than this? So I'll bring the terminal into the corner of the screen. So as you can see, we are reliably receiving the data. What I'll do now is try increasing the rate at which we're sending data. So we'll go up to 500, so we're now sending at 500 characters per second, and it's working fine. We'll keep going up, 600, 700, and you can see on the scope how we are starting to make full use of the available bandwidth on our RS232 link. So we're now at 800 Hz and it's still working fine. 900, still working fine, so we're looking quite promising. We're getting now to the theoretical maximum that we can possibly send at 9600 baud. So up at 950, and as you can see, we are still fine. I'll just temporarily change the character we're sending so you can see that it is responding correctly. We'll go up a bit higher, 960, 970. So we are now really getting beyond the maximum theoretical limit. So at 990, as you can see, it doesn't like that. So if I slow back down, you can see we are once again getting the correct data. So what I can do now, of course, is increase the baud rate. So I'll change the baud rate on our circuit. And I will of course need to change the baud rate on the terminal. So we're now running at 38,400, and if I start to increase the character rate, so we're at 1000 characters per second, 2000, 3000, so we're at 3500. And as you can see, the system is still perfectly happy. It will run at absolute maximum speed. Because the system is so efficient in terms of the only thing the Z80 has to do to load the data into it is just write value out to a single port address, that will not only load the correct value into the shift register, but it will also start the transmitter running. So a single instruction is all we need from the Z80 to load and start the transmit. Much more efficient than using a UART or a PIA and UART combination. I'm just going to go back to 9600 baud. I'll change the terminal as well. So as you can see, once again it's working the way it should, back up at 900 characters per second. But of course we have the second part of the circuit, so it is a full duplex system we have here. Now this button that we have is to allow us to read the value that's on the receiver buffer, and also to reset the circuit so it's ready to accept the next data value. So I'll press the key on the remote terminal keyboard and we'll send an uppercase A to our receiver, but we'll do that while it's still transmitting it at full speed. We should see the red LED come on. That's the interrupt output line from this circuit, and as you can see, the interrupt has been thrown. So the Z80 would normally respond by reading the data, which effectively is what happens when I press this button. We should see the hex value from uppercase A appear on the LEDs, and the red LED should go out, which it does. So we're getting 4 and a 1, which is 41 hex, and that's the correct value for an A. Also, when I release the button, this will go back out. It doesn't actually delete the data, so we can come back again as long as we haven't received any new data and reread the value. So it's quite a nice flexible circuit, and again, the only thing the Z80 has to do to read the incoming data is to read in from a single port value. That will read in the data and also reset the circuit ready for the next incoming data value. We can run it at full speed in full duplex mode, and that gives us a very flexible system. We can hook it up to interrupt lines. In fact, in the next video that's what I will do. I'll hook this up to our Z80 board, write a bit of code and try to demonstrate just how efficient this is, and also how simple the code can be to use it. Much more straightforward than writing code using a UART, and also gives us absolute maximum performance for an RS-232 link. So it's not all negative when you're doing discrete circuit design. You can gain quite a lot. They are more complex to deal with, but they're probably a lot more fun to deal with, and it doesn't necessarily mean that you have to sacrifice performance. Now, we are missing quite a lot that we would normally have with a UART, for example, but most of that for my particular system I'm not concerned about. If you want to include things such as CRC checksums, that sort of thing, remember the Z80 can do that in the same way it can generate parity directly from data fed into it. You can do that within the Z80 itself. So we're not necessarily completely throwing all that away. We can still implement that if we want to. It's just up to us to do that in either more hardware or in software. But hopefully what I've got across in this video is that just because we're designing using discrete circuits doesn't mean that we're not going to end up with a system that performs well. And if anything, what we're going to end up with is a system that is very much easier to deal with once we've done the design, and also potentially will give us just as much, if not more, performance. Certainly if we're trying to run a serial data stream at full speed, this system will have much lower overhead for our Z80 than a traditional UART. Okay, well, hopefully you found that interesting. In the next video, as I said, I'll hook this up to our Z80, write some interrupt handlers and see if we can properly send and receive data using our Z80 computer.